Yeah, so I'm going to talk a little bit about SiLA, the kind of the organizational side, and I think Burkhard's going to talk more about the technical side. So let's get started. And thank you so much for the invitation. I'm really happy to be here. So I've got my banner at the top, which kind of confused me. Never mind. So in a few words, SiLA is a non-profit association established originally out of Basel, Switzerland. There's a global footprint and has been going many, many years, more than 10 years. It's here to establish international standards on open connectivity, specifically for the lab, to support lab research, lab automation. It's got individual members who join for free. We have about 4,000 of those. And we have core and supporting members who are organizations who pay a membership fee, which helps to fund our operations. The standards we develop are all available free of charge. There's no license fee involved. There's a license terms, but not fee. The aim is that it's low cost of ownership for all stakeholders, users and vendors and others. And I'll go into this in more detail, but just as a snapshot, that's where we start from. So we've long worked to try and align the interests of three major groups. That's the users, the lab owners, whether they're in the pharmaceutical industry, other industries, or even academics, research. And they have specific needs and expectations of lab systems, that they work well, that the devices work well together, and that innovation is possible. And that's, of course, quite challenging when you wish to exploit all the different devices from many different suppliers. We also have the supplier viewpoint. We try and align their interests so that they can supply their devices, their clever optical, physical devices, to the lab users in ways where they can be productive very quickly. So a simple interface, they can focus on their work and not have to play too much around with the IT interface issues. And then the third category that we've worked hard to align with is the integrator, who has a somewhat challenging task of bringing multiple devices together into a system that will work for the user. And the user's needs change, and the money is required, and the timescale changes. So those three viewpoints are often quite difficult to align, but that's what we worked for. On the right-hand side there, you'll see logos of our current corporate members. You may recognize some of these. Roche, Novartis is where we grew from, internal projects. You may also see people like TCAN, whom you'll surely know, and also some universities and some companies you won't recognize who are startups. So academics and startups are actually very, very important in this ecosystem. And up until the last few years, I think we've been somewhat neglected by us. So now we're trying to align the interests of all five groups, which presents new opportunities, new challenges, but it makes for a very exciting and dynamic field. In terms of what happens under the hood, SiLA is a communication broker. It's about communications. Sometimes I compare it to USB for the lab. It's not the cables and the little logo and the plugs and all the problems with that, but it is a peer-to-peer communication system, service-oriented, and it's based on modern web technologies. So these are technologies, HTTP2, XML, gRPC, technologies you probably use every day. You certainly use every day, and you probably use every hour, because they are the underlying basis of the net and the web. The open standards, as I said, no fees, no royalties. And you'll hear later on about AnIML, which is around communicating the data, but this is the broker that sits a bit below that. The standard is the main job of SiLA as an organization. So we develop the standard, and we have a standard document. I have one not with me today, but it essentially describes in three parts, three sections: a core, which is a framework of the concepts. There's a mapping of the concepts to concrete technologies I've spoken about a moment ago. And there's part C, which is an extendable part. There was a SiLA 1, or SiLA 2 now, SiLA 1, which was not extendable, and we learned a great deal from that experience. So now we have an extendable framework, which will evolve and will stay at SiLA 2. Accompanying the standard, we have a governance process. You may be familiar with those that exist for ISO, ASTM, and others in Germany. As a non-profit industry association, we don't have to be burdened by all the heavyweight process of that, but we have a fair and balanced process that allows the standard evolution to be balloted with our members. We have a community of developers around us who develop reference implementations. So SiLA as an organization encourages this, and then on GitLab you will find open source with 4 full language bindings, talk about in a moment, and some experimental additional ones. So it's a community that develops the code. It's the organization that develops a standard to which the code will support. We have in the day-to-day a core working group, excuse me, led by our CTO Daniel Euclid, and this meets every 2 weeks or so. We're at number, I think we're at 240 now last week. So we keep that going. We need to respond to requests and changes and questions, and we keep that going very, very well. We also encourage our members to think about new directions, and we're very lucky to have been joined a couple of years ago by Adam Wolf from Takeda, who decided that, or told us that we were not paying enough attention to the modern robotics, which you'll see in many factories and facilities, and even in some labs. There's a lot of great stuff happening in robotics, but it's not been very, very well connected to the lab world for most labs. So we created a new robotic working group. There's a framework there which allows that to be connected to what SiLA does. And within that, there's a labware ontologies working group, which is also very important, but also very challenging. Also, in the last year, I think we've got Tim on the call. We've been very lucky that Tim Meyer has joined us from University of Göttingen and pointed out that adoption is still quite challenging for those who are not of the very high level of IT expertise. So an adoptions working group has been started, and they've been working on an installer, which I think is now released or very nearly released, to allow people to come into the SiLA community and start benefiting very, very quickly, much more easily than before. And the newest working group is on cybersecurity. Summer just gone. We're lucky to have Unilever with us as a core member, as a user, and as a consumer products company. They come with a very fresh approach and very, very motivated to protect the lab from cybersecurity in ways that maybe some researchers were not so worried about in the past. So that's bringing another wing to our beast. The governing board of SiLA, it's important to highlight who we have here. We are real people. We are faces. We are responsible for the management and the governance of the association. And one key point here is that half of those people are from industry. So we have end users, and I just got at the bottom that numbers are out of date since we have Novo Nordisk, which is one of the biggest companies in Europe. So we've got a huge market capitalization represented in aggregate, staff and sales. So 4 very large pharmaceutical companies, Unilever as well. So very, very heavyweight. And it's super important for us to listen to what users want, research users within those organizations. We're not about playing the things. We really want stuff to work and be used out there. Oops, I think you've seen that already. And in terms of activities that SiLA is involved with, there's a number of different things. The working groups I talked about. We do encourage a lot of collaboration, but because we have the vendor side and the user side in our community, we're often having to field questions like, I really want one of these. Do anybody know anybody who can help us? In some cases, there's already a SiLA device out there in prototype form or in test form that can be used, and also feeding back and connecting what users need on a day-to-day into the vendor community and the innovation community is very important. We have a business activity side as well as a technical. Primarily we're technical and standards, but I know personally that we've brokered a lot of business, and that's good news for everybody in the community. In practical terms, we have the working group, so people can join that. To lead a new working group, that's typically responsibility we only allow paying members to initiate. We highlight awareness around use cases, around products and about benefits. We have some training I'll talk about in a second. We organize hackathons, we have application notes, and we have a shop window. So there's a number of SiLA supported products. And even we as hosts to the GitLab facility are often finding that there are new products that have been released. The last trade show I was at, I bumped into some booth holders who had, yeah, we know SiLA. In fact, we've got it in our products. Here's a flyer. So it really is more dynamic than we sometimes realize. Last few months, we've released something called Awesome SiLA, which is a list of the facilities, the implementations, the drivers, the clients and devices. And that's great examples from which people can work. We have an active Slack community where you can go in and ask questions. So really all of that infrastructure that allowed coders to talk to users, to talk to people who are maybe part-time programmers, who are maybe scientists and want to do the job. So very, very rich interactions between different members of the community. There's the training materials we support. We have some material that supports the 4 language bindings, so C++, C#, Java, Python, and that 4th one along, if you don't recognize the logo, that's the TCAN implementation. TCAN have been with us along for a very long time. One of the issues around open source libraries that people ask us is, what's the quality of the code? If you're a programmer, if you're in a research environment, that's maybe not a huge headache. If you're a commercial company with shareholders, that is very important to have a good answer. And what TCAN have decided to do is take a clone of a library and maintain it themselves. They promote it to their third-party partners. They have a big integration business, but it shows a business model which is completely compatible with open source code. So we include that among the implementations, even if the SiLA community alone does not own it. It's TCAN corporate that own it. And I'm just going to close with a few examples of uses that these different categories of members have, projects they've carried out to benefit from SiLA. So in terms of the large end users, as I said, Novartis, Roche with a start, Takeda, Novo Nordisk have joined, Unilever are bringing us in, and we also have some smaller biotechs that may be less well known. And as I said, we brought in the university facilities, Kiwi Biolab, you'll know well through Mark and others, and EPFL in Lausanne have a great catalysis facility, and we're working closely with them. Because I think universities have always been the place where innovation happens and new people are trained, but now with some of the geopolitical priorities and the national priorities in terms of funding, there's some very large and very impressive facilities being created where really the boundaries between industry and research are starting to break down, and communication and collaboration is possible in a way it wasn't maybe 10 or 20 years ago. I'm just going to peep this up. It's a video. I'm not going to play the whole thing, but just to show you one of the things that our users have got is this is a mobile robot that wanders around a lab at Idorsia in Basel, and it's a mobile robot with a classic industrial robot arm. And hop to the middle. I'm not going to play it because it's going to take up too much of the time. But what you see is it picks up cells from an incubator, and which is a SiLA-enabled incubator, adapted, talks SiLA. It talks to a fridge. It talks to a hood, which is SiLA-enabled, SiLA-modified. And inside the hood, you may be able to see a liquid handling robot arm, which is all SiLA-enabled. And the robot is from a SiLA member, so it's SiLA-enabled. And there's an overall orchestrating program, which is also SiLA-enabled. So there's about 6 or 7 devices there that were put together, all thanks to the SiLA interface. And one interesting part of the story is that the startup company that produced the orchestrating software decided to change strategy because of its funding and its management and direction. But because normally that would have been a disaster for the system because you lose the controller. But because it was all through the SiLA interface, another member of the SiLA community could come in and provide an orchestrator and a controller. So it was only down a very, very short period of time. That's one of the benefits of SiLA, which we don't normally talk about too much, but is definitely there. I'll move on from here. Whoops. Pick out 2 examples of users exploiting SiLA for closed loop labs. So this idea of you've got a lab, you've got some AI, you've got some robots, and where the robots are driven by a recipe, but the recipe is informed from the last iteration and maybe informed by the literature or the AI and the last piece of work. So Novo Nordisk in Denmark, and they've got a picture of James Love, who's done a 5-minute video. I won't have time to play it now. Who's done some great work exploiting SiLA to connect those devices. They developed their own SiLA devices because they weren't available. And in some cases, they published the drivers. In other cases, they've exploited SiLA compatible devices. So really, really new stuff, really new work on closed loop processing, self-driving labs. And in the bottom there, you've got a paper that was published by the University of Toronto. Canada's been very, very innovative and advanced, forward thinking in this area. And this acceleration consortium put a lot of money into developing, again, this closed loop concept, more for material science, I think. And there's a snapshot I've taken from their article, again, code on GitHub, where you see SiLA as the connector, the glue that allows those different devices to be brought together. Moving on, just to say a word about the vendors. So some of the key vendors are Aztec projects in the UK. You saw their robot, AST, who provided kind of a dashboard, USB SiLA hub that's been very popular, certainly with Unilever and others. Promega make a plate reader, which is SiLA native. Some of the others, and at the bottom, again, pictures of the SiLA fridge and the SiLA incubator. That's actually the fridge, where it's just a fridge is a very banal device, but to get a robot to use that, you have to tug quite hard to open it. It's beyond the capability of many robots, and then the robot arm will get in the way. What's happened there is the startup put together a little door opener lever you might find in supermarket or shop doors, controlled by a SiLA box. So very, very quickly put together automation of the fridge to allow automation of the whole process. And then just to close on some of the hackathons we've done. This is a 2-day one. We were lucky enough to get funding to organize with our partners, BR Largo and Constance, and bringing in the precise arm and the UR, Universal Robots arm, not too traditional in the lab, getting the two to coordinate together the coordinate frames and hand over plates from one to the other to reading. There was about 30 people in that, a lot of pizza consumed, very, very nice experience in a villa just by the Rhine River. And this is a photo from Burkhard, you'll see in a moment, the SiLA Splash, which is a kind of open hackathon format that we use, introduced to SiLA, introduced to AnIML, and then depending on who we have in the audience, managers, product owners, researchers, programmers, we can then go into depth into the code and give an example. And within really 5 or 10 minutes, we can code things up and have a discussion about how it fits best to the particular person's needs. And we can do that on site as well. We've curated collaborative booths. This is from Future Labs last year, year before last, where again 8 different vendors came together with SiLA. And going back, SiLA as a partnership, we work very, very closely with a number of organizations, commercial trade shows, commercial conferences. We're not proud, even if we're non-profit. I'm very, very happy to be in this room today to see how else we could extend our collaboration with other people who are new to us, for whom we are new, just to move things along, to make innovation swifter, less painful. And I think that's where I'm going to stop. Sonia, back to you.
Great, thank you so much. As far as I understood, Mark will now go into the presentation, or is Burkhard also showing some slides?
I would suggest that Burkhard continues because it's more important, and then
okay, great.
My demonstration is very short, like 5 minutes.
So thank you so much, and I think we will have a joint discussion afterwards when we see the full package.
Sounds good. Okay, so
yeah, it works. I see a toucan. Wonderful.
Wonderful. Yeah, the toucan is important, right?
Okay, yeah. We also have a toucan code.
Excellent. So thanks also from my side for the kind invitation to be part of this Stammtisch, and we're very excited to discuss with all of you. And I'll pick up where Patrick left off and talk a bit about how SiLA does the things it does, and then add a bit of how AnIML fits into that. And while SiLA is the communication protocol, and AnIML will then provide us with a mechanism to document the outcome of experiments and the execution of experiments in a data format. And as we know, data and communication go hand in hand, so let's also look at it that way. So how does SiLA 2 handle communication in the lab of the future? Well, it's all about the generation process of the data. And Patrick already talked about the organizations. I'm not going to talk about that very much. I'm going to focus on how SiLA does the things it does. So if you think about the SiLA setup, it's designed to be a microservice architecture for the lab. So it's based on HTTP2, it uses gRPC, as Patrick mentioned, and it combines a couple of other standards in a meaningful way, so you can learn from what has been possible in other domains. So the first issue that you've got is you need a common communication protocol to be able to talk to different instruments. That's where HTTP2 and gRPC are going to fit the bill. But then when you have an instrument in front of you, how do you know what it can do? And that's what the standard protocols out there don't give you. And that's where SiLA offers what we call feature definitions. A feature definition is a way where an instrument can describe itself. It can say, this is who I am, and this is what I can do. So in other words, these are the commands that I offer. These are the parameters, these are the return types, and this is the documentation about what each command means. And these are the properties, and this is how you can subscribe to them, and this is how you can get events or updates on values and so on. So feature definitions allow me to look at a given instrument and get a machine-readable definition or description of its capabilities, so that I do not have to write custom code in order to interface with that equipment. And that's a game changer, obviously. And if you have a platform that's able to parse such a feature definition file, which is just XML, you can learn how to talk to that instrument even if you've never seen it before. And that's wonderful, obviously, if you want to integrate things on the fly and you want a quick time to deployment. So that's the first bit. It's the feature definitions that allow me to describe the capabilities of an instrument. Then there is another bit, which is feature discovery. What feature discovery allows me to do is, and that's where SiLA offers well-defined commands of how I can get the feature definitions out of an instrument, right? So while a feature definition is just a file and says, this is what that service does, the feature discovery allows me to talk to a device over the network and ask it in a well-defined way to present its features to me. So I can even do that introspection on the fly the first time I see that device on the network. And then comes the third bit, which is, well, how do I know where on the network that device is? Well, that's where SiLA server discovery comes in. That's based on zeroconf or multicast DNS, which is what we use all the time to find our printers at home and to find our loudspeakers and so on. In fact, that's also how AirPlay works to find its peers. And what SiLA has done is we've sprinkled in an additional device type to make that work in a lab environment. So you can discover your SiLA servers, and then you can ask it, well, please describe your capabilities. And then you have a common way to describe those capabilities. And that's how you ensure plug and play. And that's how that works. And so you can tell the instrument what you would like it to do. And at the end, you're getting some results back. But what about those results, right? So it's nice if we have a common way of talking to our instruments, but we should also then think about, well, how do we store the data that comes back? And that's where SiLA's job is done and AnIML's job begins, because that then gives us an open format for handling all of that instrument data. And that can be analytical data, biological data, process data, and so on. And that's why that partnership between SiLA and AnIML makes a lot of sense. So let's switch gears now and look at it from the data side. So we all know the pain points in lab data management. We have so many different proprietary file formats, different measurement techniques, different vendors, and that gives us little choice in software tools. And what's even more difficult is to document multi-technique experiments that use multiple techniques, and I want to get that into one common data set. It's really hard. How do I share that data with the point of use? How do I exchange data with internal and external partners, and so on? So that's where you have a very clear rationale why data standardization makes sense. But at the same time, we realize that we are in it for the data, because the results, the data, is the most important outcome of our work in the lab. So we should really do more to make that data as accessible as possible, because that's what generates the value, right? It's the integration between systems, it's data analytics, exchange data with partners, the long-term data retention, and the data reuse, the FAIR principles, in other words. And we believe that the more accessible we make our data, the more it will be used. And the more accessible we make our data, also the less it costs to use. Because there is a cost of access. There is always a certain effort that I need to put in order to use the data. And we want to reduce that effort to make it really straightforward. And AnIML does that using an XML-based approach. It stands for Analytical Information Markup Language. It comes out of ASTM. It's intended for analytical chemistry data, was then enhanced to support biologics data and process data as well. It was put together by a consortium from industry, academia, vendors, and government entities. That effort started in 2003. So a lot of work went into creating the data model that is there now. And we're really pleased to see that that data model has really held up very, very well over the test of time. And has been useful to adopt for more and more techniques over the years. So how does AnIML do this? AnIML is a two-tiered data representation. So first of all, you've got what we call the AnIML core. That's an XML schema that offers a generic data container for any type of analytical and biological data. And then you've got a a level on top of it, which basically gives you your data dictionary or your taxonomy, where technique definitions define how you use the data format to store data for a given experiment type. And you can then create experiment steps that reference these different technique definitions, and you can then create AnIML documents that combine experiments of these different types in one document. It supports data from multiple analytical techniques, even combined in a single document. And that's where you have a really, really powerful capability that makes a lot of sense in a lab setting. And that's really hard to achieve without something like AnIML. It captures not only results, but also sample and process data to ensure reproducibility, because obviously the reproducibility of science is really, really important. And to be able to make that reproducibility happen, even across multiple techniques, used to be a really tough problem, and still is. And with AnIML, it gets a little bit easier. It's extensible by vendors and end users. And for the regulated communities, it has things like audit trails, digital signatures, and validation capability. And you will notice that in all of the design decisions, we've put a strong emphasis on data accessibility and easy adoption, which leads to a low total cost of ownership, because obviously there's always an effort associated with handling that file. And we need to really drive that down. So how does AnIML actually work? Well, this is the AnIML experiment model, and it's modeled exactly after how a lab works. So you would start with some piece of material, typically a sample that you want to do something with. Let's say you want to analyze it using some measurement technique. So you are then saying, okay, I've got this sample, and I've got this experiment step that is consuming that sample, or that is using that sample. And that experiment step says, okay, I'm doing, let's say, a UV-Vis spectrum. Okay, and I'm using this sample. Fine. But in order to know how to do that, well, I need some instructions, right? So this is my instrument method. This is my configuration. There are different names for that, right? And so if you have those two things, if you know the material and you know your method, then you have a reproducible experiment step. Yeah, and out of that experiment step, you're going to get some results. Those results will obviously depend on the analytical technique. And here we're going to get a UV spectrum. That's fine. But some techniques not only produce results in terms of data, they also produce new materials. So let's say I'm doing chromatography and I'm collecting fractions, or I have a bioreactor and I am taking a sample once a day, yeah, or I'm harvesting and things like that. So at that point, you have a material flow at the top and you have a data flow at the bottom. And now you can use these experiment steps as individual steps in an overall lab workflow. So if we make a bit of room here, that sample that we have now extracted, let's say, by collecting a fraction from our chromatography, we might then actually feed that into another experiment step to do further analysis and so on. And this way you can create a complete workflow that spans as many pieces of equipment and techniques that you would like. And that makes AnIML really, really useful. Do you always need these complex AnIML files? Oh, no. Yeah. Some people just say, hey, here's a single chromatogram and that's it. Here's a single spectrum. That's it. Here's a single rheology measurement. That's it. Yeah. And others say, I am doing an entire formulation which contains 20 steps and it combines 15 ingredients. And I have some analytics that happens on the material that's being produced. Yeah. So AnIML can take on the level of complexity that you need for the lab workflow and activity that you want to describe. The specification is also open, so there is no royalty for implementing that. It captures data across different techniques that are required. So sample, method, and workflow description, the instrument, the operator, the results, and all the necessary identifiers to relate the information back to the original context. You can have these multi-experiment workflows together with a material and a data flow. The format is human readable, so even without software tools, you can do something, but you do have a great selection of tools already out there today that can be leveraged. And here is an example of what AnIML looks like for a couple of different measurement techniques. I'll show you some in more detail. This is the list of techniques that we know about. We don't know about all of them, yeah, because people are free to add their own technique definitions. But obviously, we want to curate these a little bit and create a platform for sharing these. And so you've got the analytical chemistry domain, yeah, with chromatography and spectroscopy. You have what you need for large molecules, and then you've got some others that are there for, yeah, a bit more in the material science and analysis space. And yeah, we're adding more techniques all the time. Some examples here, starting from HPLC. In this case, we have exported this from thermochromeleon together with peaks and everything. Here we've got UV-Vis. In this case, it's Perkin-Elmer with spectra, with method information, with sample attributes coming from a LIMS. Same data format, same tooling. This is what plate reader data looks like, also from Perkin-Elmer. And this is what Raman data looks like, in this case from Analyze IQ. And you always see, okay, these are the experiment steps that I have in here, and you've got a nice rendition of that. Or if you have something more complicated, like antibody purification with FPLC, this is Cytiva Unicorn, where you have multiple detectors that come together, and fraction tables and things like that. So you've got different fractions that get produced. You've got the sample that is loaded on the column. Or if you've got mass spec data, works just as well. Or in this case, it's NMR, whether it's FIDs or whether it's spectra. And this is from Burkhard Topspin. And this is actually a combination of multiple. You have a bioreactor here from Sartorius and a Roche cell counter, the ZX Hi-Res, and you overlay them so that you can actually trend the process. And all of this, comes back to the same simple syntactical structure where you say, okay, I've got this sample, it's got this ID, and then you've got these parameters with different key value pairs. And if you look at this for a couple of seconds, you can already spot the structure. And not only is this machine readable and very powerful, but it's actually represented in a very simplistic way when you actually store it. And that's a really nice combination, right? It's powerful, but it's simple at the same time. And that makes the data very accessible and nice to reuse. And that's what we were trying to do in the first place, right? Get the reusability of our data. And what's also important is the significance of an ecosystem. Yeah, if we build lab standards on existing IT technologies, that opens up the respective ecosystems to the lab. We've seen that with SiLA, where there are tons of libraries around that help us deal with gRPC, with HTTP, with protobuf, and there are lots of developers that know that technology. And with XML, it's the same in AnIML. And so we no longer need to build bespoke tools for the lab, but we can use mainstream IT, and that reduces complexity and total cost of ownership. And we can just use whatever XML tooling we like. The expertise is widely available, and so I can stick an AnIML document into Crystal reports, and it'll display a peak table. Or I can feed it into Power BI or SharePoint, and they know what to do with an AnIML document. So those are the synergies, and we're trying to really cultivate the interoperability between those ecosystems. So if you put the two together, then you get something really nice. So you've got the connectivity coming from SiLA as a communication standard and the data model, which is AnIML. And so if you put them together and you've got something like a LIMS that wants to control equipment, you can now really go through the entire process. So you would do SiLA 2 discovery first, and that tells you, oh, I have the following services here. I've got balance, I've got a chromatography data system. So these services respond, and the LIMS can inventory them. Then, since those instruments and services can describe their capabilities, they say, oh, I have the following feature definitions. So this is what I can do here on the balance side, weighing, way to target, open, close door, and so on. Where a chromatography data system would obviously have something like submitting a sample or an entire sequence or batch of samples, reading the audit trail, and things like that. And at the same time, you can also describe what the data will look like that these systems will return. So the technique definitions for a balance, or the technique definitions in the AnIML side here for chromatography. And so the LIMS learns how to communicate, and it learns what the data structures are. And that allows me to then use SiLA as the communication vehicle. And in the end, I get a complete and traceable AnIML data package describing what each of those components did. And that's obviously very useful. And this works with zero customization required, no parsers configured, and so on the LIMS side. And the LIMS is obviously a placeholder for any other leading system that is trying to go the last mile. And I've deliberately chosen two very different kinds of instruments here to really show the generic nature of this. So just some interesting use cases of AnIML in the wild. And Mark is obviously going to show us a couple of things later, so I don't want to spend too much time on all this. So first, what drives adoption? Well, if you really have benefits for all the stakeholders. Yeah, we're doing this for the users and the vendors. We're not doing it for ourselves. So the standards must have a lower total cost of ownership than a proprietary alternative. Only then it makes economic sense to do this. And standards will be adopted if they solve a concrete problem, to allow us to do better science, to increase compliance, to increase flexibility, to reduce cost, and so on. And we always have to keep that in mind as the folks who define these standards, that this is not only a technical problem, right? It's also a political and a business aspect that needs to be taken into account to create opportunity for everyone in the ecosystem, because only then it will thrive. So we've got all kinds of examples from different LIMS and ELN and automation platforms. And Patrick also mentioned a few, and I've got plenty of screenshots here. I just want to pick out a few. If you're looking at the LIMS market, for example, the LIMS guys are always on the receiving end of data, right? Because they are interested in the results. And so just examples from some of the top 3 players in the LIMS space. So we've got systems out there running that use Lavantage with great collaboration with Lavantage, where we've been able to get bidirectional instrument integration with SiLA and AnIML going for also including chromatography data, sequence submission, embedding viewer technology directly on the sample entry screen. Really, really nice. And here is an approach with Labware, which is the LIMS market leader, where you also have the possibility to get data in, and they have a downloadable module number 630 that you can get from Labware DevTrack that includes AnIML result capture, and they also have a viewer integration, and they have a dedicated set of scripting commands that know how to deal with AnIML. And this is a very quick integration that took less than 2 hours to get Thermo Fisher's platform for science into a position so it could consume AnIML files and also render them. And that's because it's an ecosystem that, where you have existing tooling available, and getting data out of XML is not that hard. And so, yeah, we're really looking forward to creating those value propositions together with our friends in the vendor space. And if you look at the overall lab informatics market distribution and you add up the different market shares, then you're at a point where you can consume AnIML content with over 51% right now of the market, which is something that we're really, really happy about. Does it all come naturally? Does it all come for free? And is there zero effort? No. Yeah, there's still work involved, but it's possible. And we've seen a lot of these deployments now in practice. It's taken a long time to get there, but now we're able to see the fruits of the labor. We're very, very happy about that, and looking to build this out even more. Now it's more of a governance thing. It's less of a building thing. Yeah, and we don't want to stir the pot too much. We like stability because stability will help the ecosystem. So we're very careful about the changes that we're introducing, because we want to protect the investment of the folks who are building on this. Yeah, so we're taking governance very, very seriously, and I think this is and it shows here. So that's it from my side. Thank you very much, and I'll hand it over to Mark now for some real life action.
Okay. So yeah, let's immediately start because we've not so much time. So I would like to show you this thing, this instrument here. This is a small lab instrument I'm using here in the lab. It's basically an Arduino and a thermistor. And why I'm showing you this instrument? The reason is you might ask, yeah, well, what's the point of SiLA? Of course, there are vendors available, and I show you in a second when my screen shows up a list of available vendors. So do you see it now? My browser. So if you go to the SiLA web page, which I to put in the chat, which I put in the chat in a second. So there it is. If you go to this web page, you can browse already available SiLA devices. So So as Patrick and Burkhard tried to explain it, it's already building up infrastructure and it's nice. But the question is, what if you don't have if you don't have a SiLA device? And this is something I would like to address here. So how can you build one? So if you don't have natural support, of course, we want in the future that every device speaks SiLA, or at least an open standard. There's another one, OPC UA. One of these standards, so it must be open and must be needs to transfer metadata in a very convenient way. Is useful for fair data in a very generic way. So, and I'll try to demonstrate to you now how to make like any lab device that has some kind of accessible interface into SiLA device. So, in the overall idea looks like this. So, you have then a lab device, so whatever that is, and we have in SiLA. So SiLA provides a software development kit, or not only one, but for the most popular language, as Patrick and Burkhard explained. So Java, JavaScript, C#, C++, and of course Python are important. We provide these software development kits, and with these, it's very, very simple to make any device into a SiLA device. The only thing that you need is the specification, the communication protocol of this device, and then you have infrastructure to build in a few lines of code a working SiLA device. And this is what I want to demonstrate to you. So I have here this SiLA Arduino with a thermistor, so a simple thermoresistor, which can be used as a thermometer here in the lab. And then what you can do now, if you have then this SiLAnified, you can, for example, capture the data in a time series database. And this is something I'll also show you just as an application. So you can already, so if you have a SiLA device, you can use our open source lab data aggregator and aggregate the data and capture the data in a time series database, monitor the data. You can use a universal SiLA client as the one from United Labs, but there are several ones, which I also demonstrate to you to explore the machine. And you can then funnel this data into databases like the Lara database or whatever. I mean, it doesn't matter. And you can, if you have like semantic data, I mean, one of the types Burkhard explains, so AnIML kind of semantically structured data, or if you have RDF data available through your SiLA device, you can store it in a triple store. So this is not what I show you. If you are interested in this more advanced stuff, please contact me and I'll give you an introduction to that. So now let's quickly show this in action. So I'll switch, switch to my browser. So I just plugged this little Arduino into my computer USB port, and then what you get here, what you immediately can do is you can start the SiLA browser, which is now open here. It's an open source tool, and you can go to and you see here all the SiLA devices that are running in my network. So right now it's the SiLA data aggregator and the thermistor thermometer. And then you can, as Burkhard explained, you can explore already the device in a generic way. So you can, for example, get the server name, is it thermistor, is it the server type, is it the server description, you get the features, so all the things that this device can do, a list, and you can get much more here to explore this. What you can also do is, for example, you can explore the temperature here already in this. So I didn't program anything here, just that you understand. So once you have like a SiLA device, you can just plug it in and start a SiLA browser, and then you can communicate with it. So if you want now the current temperature, I can subscribe for the current temperature, and get the current temperature. Yeah, sometimes I have a problem with the connection here with the USB connection because I'm moving it. So I keep it. See if it reacts. So of course, this is not very useful if you want to capture data. So what you then can do is you can run a data capturing tool like this one. This is an influx database, and what you see here is the current temperature that is coming from the device. You see, there's I accidentally removed the USB plug, so there's nothing coming. So I don't know if I have the time to restart it, but you see the idea. So you basically plug your instrument into your computer, start your SiLA environment, and you can, for example, monitor the data, capture it, aggregate it. So in this case, with this lab data aggregator, we can squeeze the data into one, so we can combine a lot of time series data into one file. And that can be either an AnIML file or it can be a JSON LD file. And the nice thing about it is if you have some semantic knowledge ascending from the device, or some semantic information will also be captured in these databases and will be explorable. So that you have, and that's the most important message. You can build up semantic knowledge-based information from the bottom up. So you can build up devices that explain themselves, that tell, I'm a thermometer, I'm measuring temperature according to a certain ontology, and you can point to this ontology or to this very deep definition of what is measured. I'm measuring temperature. You can point to the temperature specification of what the temperature measurement is about. All these things are now available as an open source solution and can be very powerfully combined to larger workflows and even higher experiment levels, like Burkhard explained to you. So it makes it very powerful once you have an open source standard. By that, I stop here and give you a chance to ask some questions. Thanks again.